This is chapter 5, problem 34. It says a fluid flows steadily in the x direction, indicated by this arrow, through a control volume. Should probably indicate that we have a control volume here. So we have a control volume. Oh shoot, that's not a control, that's a control surface. Whatever. Anyways, this is a control volume. And measurements indicate that to cause this flow, the force acting on the contents of the control volume is 120 N in the negative x direction. Determine the net rate of flow of linear momentum through the control surface.
Big wheels keep on turning.
Let's redraw this control volume as a little more accurate. So we have our control volume. And determine the net rate of flow of linear momentum through the control surface. Alright, it references equation chapter 5, section 2, equation 2, which is the partial derivative with respect to time of the integral over the control volume of the velocity times the density with respect to the velocity or volume. That might be volume. Plus the integral over the control surface of the velocity. Is this supposed to be oral? Okay, I'm sorry. My professor has the worst handwriting. Okay. V rho times the velocity again times the dot product with the n hat direction derived with integrated with respect to a equals the sum of forces on the control surface, a control volume. Excuse me. This is a great one to practice what the difference is between a control surface and a control volume. Alright. For steady flow, this whole section right here goes to 0. Okay, that makes some sense. Honestly, I'm a little bit confused by this myself. Okay, so this all goes to 0.
My Japanese professor
and
is a little more like Sanskrit.
It is known that the net force on the control volume is equal to negative 120 N in the I hat direction. Okay, so equation 1 is simply this equation, or this function rather, this integration over the control surface. This is the net flow of linear momentum. Just to abbreviate, I'll call it MV because that's usually how it's represented. Linear momentum through the control surface. Alright, it's also equal, from this equation, we also know that it's equal to the sum of forces on the control volume, which equals negative 120 N in the I hat direction. Alright, the dimensions of rate of flow of linear momentum are force. Okay? Because linear momentum itself is in terms of velocity, but we're talking about rate of flow. So that's actually going to come out in newtons, and that is correct. Okay, so I don't know what he's doing here. He's solving this, it looks like. L over T times M over L cubed Oh, I see. He's doing the MLT method where he's solving to determine what it is. This is part of his note. So we've got length per time. This is meters per second times kilograms per meter cubed. That's density. Again, times the velocity times a direction times the area. That's where that bit comes from. N hat is really doesn't have any. It doesn't have any units. It's not supposed to change any magnitudes. It's only supposed to change direction. Oops, that's not where it goes. That goes there. There we go. That was supposed to go there, and then this one was supposed to go there. And this is just him double checking mass times length divided by time squared is an indication of force. So the units of force are correct. Okay, control volume versus control surface. Dang it, I had to figure it out again. Alright, I'm sure that this equation right here, no, this is a specific one. This is a specific adaptation of something else. So don't worry too much about memorizing this. It probably applies to something that you do need to know, but as we keep going, we'll probably encounter it. Get it all one of these problems done.